last page of your review includes three fairly challenging problems. So let's start with 14. It says two congruent circles and two parallel lines. So here are the two congruent circles, and here are the two parallel lines. Intersect in a total of 5 points as shown. You can see the 5 intersection points of the circles and the parallel lines. The inner segment of each line is 6 centimeters long. So that's shown here and here. Using pi as approximately 3 14/14, find the area of the shaded region. So this region that's shaded. I think the key to understanding this problem is thinking about the centers of these circles, and then realizing that if this line segment is 6 centimeters, then this line segment is 6 centimeters. Because once you realize that, and since the circles are congruent, these must each be 3, and what's represented here now is the radius of the circle. So if that's 3, then this is 3, and so is this. The radius is the same at all, no matter where you draw from the center to the edge. And if these radii are 3, then really what you're looking at here is a square, a 6 by 6 square. If you wanted to find the area of the shaded region, you would find the area of the square. I want to find a way to show you the square I'm talking about without messing up the picture. Hopefully you can see it, but maybe I can. Let me try this. When I'm talking about the area of the square, this is the square that I'm talking about. Can you visualize that? If you take away, see, the shaded region is the square minus these 2 half circles, minus these 2 semicircles. But if you're subtracting 2 semicircles, you're subtracting 1 full circle. So it's the area of the square minus the area of the circle. The area of the square is just side times side, and the area of the circle is pi r squared. The side of the square is 6, so 6 multiplied by 6 is 36. And then we are approximating for pi using 3.14. Multiplied by the radius of the circle is 3 squared. So minus 3.14 multiplied by 9. 3.14 multiplied by 9 is 28.26, but let's just do it. So 36 minus 28 and 26/100ths. Um, 7 74/100ths. Square centimeters is the approximate area. I say approximate because again we used an approximation for pi. 7 74/100ths is the approximate area of the shaded region. Problem 2. Rectangle ABCD. Trace that. Rectangle ABCD. So if I go A to B to C to D, here's the whole rectangle, the big rectangle. It's partitioned into 5 squares as shown. So we have 3 different size squares. I'm going to call this square 1. I'm going to call this square 2, and I'm going to call this square 3. The length in centimeters of AM, so now we're talking about line segment AM, which is this line segment, is a whole number. So whole numbers are start with 0. Of course, we can't have a line segment with length 0. But 1, 2, 3, 4, 5. These are all our options. 1, 2, 3, 4, 5, 6. No decimals. No fractional parts. The area of rectangle ABCD, so the whole big rectangle, is greater than 100 centimeters squared. Find the smallest possible area of rectangle ABCD. So there's lots of ways to do this, but I believe they're all going to hinge on trying to sort of understand what happens when you change this line segment AM. So I want to make a table to organize my ideas here. I'm going to place the length of line segment AM as the first entry in my table. And then I'm going to say the area of square 1, the area of square 2, and the area of square 3. And then the area of rectangle ABCD. So we have to recognize that since these are squares and all the sides are the same, you have to sort of visualize that square 2 is made up of, if you extend these lines, if this is 3, this must be 3. Do you understand what I'm saying? If this is like 3 multiplied by AM, whatever AM is. And so this must also be 3 multiplied by AM. So there's, since I'm trying to make this perfect in this, since area 2 is also a square, so this has to be 3 by 3 like this. And then since we have 1, 2, 3, 4 AM across here, this must be 4 AM. This must be 4 times whatever AM is. So you can sort of imagine area 3 being a 4 by 4 square. If you just continue to extend these horizontal lines, you know, if it's 4 this way, it must be 4 this way since it's a square. Okay, so I think the best thing to do would be to write a formula for the area of rectangle ABCD down here. It's going to equal 3 times area 1, because I have 1, 2, 3 of these small squares. It's going to be 3 times area 1 plus area 2, that's this medium-sized square, plus area 3. But we need to understand that area 2 is equal to 9 times area 1, because it's made up of 9 squares that are the same size as the small squares. And area 3 is equal to 16 times area 1, because it's 4 by 4 of these small squares. So whatever I choose for AM, whatever whole number I choose, I'm going to start with the smallest positive whole number 1. In that case, this would be 1 and this would be 1. So area 1 would be a 1 by 1 square, or 1 square centimeter. Area 2 is 9 times that much, so 9. And area 3 is 16 times that much, so 16. The total area would be 3 of these, so 3 plus 9 plus 16 would be 28. That is not greater than 100 centimeters squared. So we try the next whole number for AM2, and in that case the square area 1, this square, would be 2 by 2 or 4, and area 2 would be 9 times that much, because there are 9 2 by 2 squares here, so 9 times 4 would be 36, and area 3 would be 16 times 4, which is 64. Then if I take 3 of these, that's 12, plus these two add up to 100, so that's 112. So that's greater than 100, and it's, you know, I could make AM any whole number, and I'm going to get any whole number 2 or larger will give me an area for the big rectangle that's greater than 100, but the smallest possible area would be this first one that we found. In other words, if I went up to 3, I think I would have 27 plus 81, 27 plus 81 plus 144. That's going to be 108, 252. So yeah, it's greater than 100, but it's much larger than this one. So we wanted the first one that's greater than 100. So the smallest possible area of rectangle ABCD is 112 centimeters squared. Okay, problem number 16. Kelly and Gabby were given the task of designing their company logo. Their design must include at least one circle, one triangle, and one square. The picture below shows their company logo design. They will cover the shaded portion of the logo with glitter. About how many square inches? And we're guided to use the estimate. Pi is approximately 3.14 in our calculations. About how many square inches will they cover with glitter? So we have to look at the shaded area and think of what makes up that shaded area. If I was just looking at this half of the square, represented by that triangle, then the shaded area would be equal to, let's just call this area 1. That's not a good idea. Let's call that the combined shaded area in this, all of this together is area 1. So area 1 would be equal to 1/2 of the area of the square minus 1/2 the area of the circle. Because if I take half the square and then subtract half the circle, I'm left with this combined shaded area, area 1. This other shaded area, call this area 2, is simply, well, 1/4 of the circle. So from here on out, I'll just use AS for area of the square and AC for area of the circle. Area of the square is pretty straightforward, just side multiplied by side. And we see one side of the square is 8, so the area of the square is just 8 squared. 8 multiplied by 8, or 64 inches squared. The area of the circle is equal to pi r squared, and it's approximately equal to 3.14 multiplied by the radius of the circle is given here. Although they didn't really need to show us that, because if you think about a side of the square is 8, then the radius of that circle that's inscribed in the square must be half that, because this side's length of the square is the same as the diameter of the circle. So that was really extra information that we didn't need, or that we could have figured out on our own. So the area of the circle is approximately 3.14 multiplied by 16. And I've done so many of these that I know what that is, but I'll just do it on the side. It's 50.24. 4 multiplied by 6 is 24, carry the 2. 1 6 is 6 and 2 is 8. 3 6s are 18. Now I'm multiplying by 10, so we'll put a 0 in the 1's place. Everything is 10 times as large. 4 multiplied by 1 is 4, 1 is 1, and 3 1s are 3. So 4, 12, carry the 1, 10, carry the 1, and 5. We were multiplying hundredths by wholes, so our product is hundredths. And just as a quick check, 3 multiplied by 6 is 48, so I feel good with my placement of my decimal. That looks like a reasonable product in this case. So the area of the circle is approximately 50 and 24 hundredths inches squared. So using these formulas, we just make one big one. Area 1 plus area 2. We want the total combined shaded area, because that's the area that we'll need to cover with glitter. It's 1/2 area of the square minus 1/2 the area of the circle plus 1/4 the area of the circle. Maybe I can make it even simpler, because isn't 1/2 the area of the circle 2/4 the area of the circle? And if I'm subtracting 2/4 but then adding back in 1/4, the net change there would be subtracting 1/4 the area of the circle. So now substituting the values we've calculated, 1/2 of 64 minus 1/4 of 50 and 24 hundredths. Half of 64 is easy enough. 1/4 of 24 hundredths is easy enough, that's 6 hundredths. But what's 1/4 of 50? 12 multiplied by 4 is 48, that leaves me 2. And 1/4 of 2 is 1/2. So really what I should do is recognize that this is 12.5 for the, 12.5 takes care of fourthing the 50, but then I have 6 extra hundredths, so 12.56. So 32, having a little software issue here, but hopefully it won't mess up the end of this video, minus 12.56. I'm creating like terms by representing 32 wholes as 32 and 0 hundredths. And I'm going to borrow, make this a 9, make this a 10. 10 minus 6 is 4, 9 minus 5 is 4. Borrow here, 11 minus 2 is 9, and 2 minus 1 is 1. So A1 plus A2 is equal to this difference, or 19 and 44 hundredths inches squared. I'm just going to pause for a second and check my key to make sure I didn't make any mistakes along the way there. No, that's correct. 19 and 44 hundredths inches squared. Okay, that completes the test review video. Thank you for your hard work studying for this test. I know you're going to do great, and I'll see you tomorrow.